GameSide.com. GameSide.com.
Hi diddly ho, neighborinos. Welcome to the lesson on 234 trees, an always balanced tree data structure. A binary search tree, BST, or a red-black tree is an ordered data structure with a maximum of 2 children. A 234 tree can have 2, 3, or even 4 children and follows the same concepts. The advantage of a binary search tree is for any node with a key value x, all the keys in the left subtree are less than the value of x. All the keys in the right subtree are greater than the value of x. The advantage of a 234 tree is for any node containing a key value of x, all the keys in the child subtrees to the left are less than the value x. All the keys in the child subtrees to the right are greater than the value of x. You can always pick a point in a 2, 3, 4 tree, and everything to the left is less than that value. Everything to the left of this 50 is less than 50. Everything to the right of this 50 is greater than 50. 2, 3, 4 trees. Things you should know about 2, 3, 4 trees. They're always balanced, and in fact, they have perfect balance. 2 levels to reach all leaves, or 3 or 4 levels in larger trees. You always follow the exact same number of levels to reach a leaf. A non-leaf node can have 2, 3, or 4 children, hence the name. This node here has 1, 2, 3, 4 children. A node can have 1, 2, or 3 items in it. This node has 1 item. This node has 2 items. This node has 2 items. This node has 3 items. A leaf never has children. All of these are leaf nodes across the bottom here, and they have no children. Leaf versus non-leaf nodes. The root here is a non-leaf node. It has items and children. The leaf nodes have items, but they do not have children. The 30, 50, 70 is a non-leaf node with 3 items and 4 children. A non-leaf node will have at least 1 item and 2 children. 20 is a leaf node with 1 item. 40 and 45 is a leaf node with 2 items. 60 and 65 is a leaf node with 2 items. And 80, 85, and 90 is a leaf node with 3 items. Let's learn some terms that go with 2, 3, 4 trees. Key 0, key 1, and key 2. Nodes contain at least 1 key and at most 3 keys. There is no such thing as an empty node. Nodes are sorted. Key 0 is always the smallest value. Key 2 is always the largest value in a node. Key 0, 30, is less than key 1, 50, which is less than key 2, 70. These examples use integer keys because they're simple to understand how 2, 3, 4 trees work. But a key can be anything that supports less than greater comparison. It could be a long social security number, a string email address. If you can look at 2 keys and say that's less than this key, then you can put it as the key in a 2, 3, 4 tree. In object-oriented programming, nodes may contain object reference that provide the key and/or comparison method. This doesn't have to be a key of 40. This could be a reference to an object that provides the key value. 0 child, 1 child, 2 child, 3 child. Like the keys, the children are numbered starting from 0. Keys and children are often stored in arrays. Arrays start at 0, so we name our keys and our children starting with 0. Like the keys, the children are sorted. 0 child keys are going to be less than 1 child keys, which are going to be less than 2 child keys, and so on. In this example, all the children are leaves, but all nodes except the root are child nodes. So nodes in the middle of a 5-level tree would be child nodes. Children are usually stored as references to node objects in the parent node. We're going to use an object-oriented programming linked list scenario here. This is going to be an array of links. Each item in the array is going to be a link to another node object. So this is a link to a node object. This is a link to a node object. This is a link or reference to a node object. 2 node, 3 node, and 4 node. A 4 node has 3 keys and 4 children. This node right here is called a 4 node because it has 3 items and 1, 2, 3, 4 children. This is an example of a 3 node. This is a 3 node because it has 2 keys and 1, 2, 3 children. A 2 node has 1 key and 2 children. 1 key and 1, 2 children. It's extremely important. Keys plus 1 equals children. If I have 1 key, that means the node has 2 children. If I'm a non-leaf node with 2 keys, I have 3 children. And a non-leaf node with 3 keys has 4 children. Number of keys plus 1 is the same as the number of children for a non-leaf node. Obviously, leaf nodes have no children. This leaf node here has 0 children. Every parent key has a left and right child. If you look at it closely, every parent key has a left and right child. What do I mean by that? 50 has a left child here and a right child there. 30 has a left child here and a right child there. 70 has a left child here and a right child there. There is a strong link to a binary search tree, or BST. Is this a new and improved BST because of balance? Some would say yes. These are BSTs that guarantee balance. This is a competitor to the red-black tree. Rather than running through the algorithms to balance a red-black tree, 2, 3, 4 trees provide even better balance, more perfect balance with fewer levels on the tree. Does a 2, 3, 4 tree equal a BST? The strong connection between a 2, 3, 4 tree and a binary search tree is undeniable. I would have to say yes, a 2, 3, 4 tree does equal a binary search tree, with the added benefit that the 2, 3, 4 tree is going to be balanced. Take a close look here. Key 0 is 30 in the root. Everybody less than 30 is going to be in the left child. Everyone greater than 30 is going to be in the right child of 30. All the keys here are going to be less than key 0. All the keys here are going to be greater than key 0, but less than key 1. All the keys in subtree of child 0 are less than key 0. All the keys in subtree of child 1 have keys greater than key 0, but less than key 1. All the keys here are going to be greater than key 0, but less than key 1. And look what happens. The 40s fall between the 30 and the 50. All the keys in the subtree of child 2 have key values greater than key 1 and less than key 2. The keys in child 2 are greater than 50, but less than key 270. Finally, all the keys in the subtree of child 3 have keys greater than key 2. All the keys in child 3, 80, 85, and 90, are greater than key 270. If this were a larger tree with more levels, everything below child 0 would be less than key 0. If I had multiple levels falling off 20 here, then all of these keys off this 20 would be less than key 0. Any 2, 3, 4 tree can be stretched into a BST. Grab the root and leaves and pull them apart. What? Look at the root of the 2, 3, 4 tree. It contains 30, 50, 70. If I just stretch that out to 2 levels, I get a 2-level BST with 30, 50, and 70. All I did is I grabbed that 50 and pulled it up and made its children 30 and 70. Any BST can be squished into a 2, 3, 4 tree. I can go back and forth between BSTs and 2, 3, 4s. If I want to take a binary search tree like this one right here, push down from the top, push up from the bottom, I can squish that down to a 2, 3, 4 tree. Nodes with 3 keys easily convert back and forth. Look at this node, 80, 85, and 90 in the 2, 3, 4 tree. It just translates to two levels of a BST, 85 with a left child of 80 and a right child of 90. In the end, you'd have to say 2, 3, 4 trees and binary search trees are the same thing. 2, 3, 4 trees are just squished versions of binary search trees. Find 65. The 2, 3, 4 find or search algorithm. Less than to the left, greater than to the right. That's all, folks. With the strong link to binary search trees or BSTs, searching the 2, 3, 4 tree is familiar. Start at the root and move down the tree, finding the key or moving down the proper link. The only difference is you have to choose between up to 4 children instead of 2 children. Once again, if you find the key on the way down, you stop. If you reach a leaf and it's still not found, the key's not in the 2, 3, 4 tree. Let's do a specific find of 65 and scan the root for the value 65. I'm going to start here at the first item in the root, 30, and make a decision on what to do. If the target 65 is less than the item 30, it is not. I would have gone to the left child, but 65 is not less than 30. If the target 65 equaled the item 30, that's not true either, but if it did, I'd return found. I found my data. If the item 30, the one I'm looking for, is the last item in the node, once again, it's not, I'd go to the right child. None of these are true, so I'm going to fall through and continue the scan to the right. I'm going to start at the 30 looking for 65 and decide that I need to move to the right and look for it there. Still scanning the root for 65. My target is 65. Is 65 less than the item I'm looking at, 50? No, it's not. So I will not go to the left child. Is my target 65 equal to the item 50? No, it's not. I'm not done yet. If item 50 is the last item in the node, I'd go to the right child, but item 50 isn't the last item. I need to continue the scan to the right. I'm looking at all these options, but I'm highlighting or I've bolded the text of the option I'm going to take. And the option I'm going to take here is continue the scan to the right. After looking at 50 and comparing it to 65, I've decided to go to the right and look at what's to the right of 50. Continuing the scan of the root for 65, we're going to set the current node to the left child of 70. Why are we doing that? Remember, step 1 says if the target 65 is less than the item 70, that is now a true statement. We need to go to the left child of 70. If you look closely at the diagram, the left child is 70. 65 must be there. 65 is less than 70. Let's go to the left child of 70. This item with its bold text is the option we're going to take. Once in the left child of 70, we will scan the child for 65. We move down the tree and continue the search /scan the new current node. This is our node now. We need to look in here. If our target 65 is less than 60, it's not. So we won't go to the left child of 60. Is the target 65 equal to the item 60? Nope, that's not. If the item 60 that we're looking at is the last item, we'd go to the right child, but that's not true either. We're going to continue the scan to the right. If I'm looking for 65, I'm going to go to the right of 60. Continuing the scan of the child for 65. Is my target less than 65? No, it is not. Forget about the left child. If the target 65 is equal to item 65, that's a true statement. We have found our match. It's time to return true. Remember, I bold text the option that I take. The search is done. We have found our 65. It's time to finish the search. Let's look at a couple of options that could have happened during that search. What if we were doing a find of 67? What would happen when we look at the key that is not in the 2, 3, 4 tree? We'll pick up where we left off. When we got to this node and we were looking for 67 this time, if the target of 67 was greater than the last item in the node, 65, that's a true statement, we try to go to the right child. But When we tried to go to the right child, we saw there was a null reference as a right child. When the search sends you to a right or left child that is null, return not found. A search of 67 on the tree would take us to this node, try to go to the right child of 65, fail, and return we could not find the item 67. 234 trees versus BSTs. Keep in mind they're pretty much the same thing. A strong understanding of how a 234 tree find and search works is critical because, just like with a binary search tree, the insert and delete operations always start out doing a find of the target item before doing the insert/delete. 234 tree insert. Inserting new items in a 234 tree is almost trivial when there is free space available in the node. What I like about 234 trees is as the nodes fill up, insert gets just a little more complex with each new scenario, and at all times the tree stays in perfect balance. Perfect means you pass through exactly the same number of nodes to reach each leaf. You pass through 2 nodes to get to this leaf, 2 nodes to get to that leaf, 2 nodes to get to this leaf. Always you pass through the exact same number of nodes to reach a leaf. That's perfect balance. Insert 25. Start with the easiest insert, into a leaf node with plenty of room. Find the leaf node the item belongs in and place it there. 234 trees inserts always occur into a leaf node. Since the target 25 is less than 30, let's go to the left child of 30. Move down the tree looking for a leaf node to place the new item. 25, what I'm trying to insert, is less than 30. Let's go down to the left child of 30. Continuing with the insert of 25, we have found the leaf node 25 belongs in. We've reached a leaf and it's time to place 25. Very important. The new item must be placed in sorted order. An item smaller than 20 means 20 would shift so the new item could insert before 20. In this case, 25 is greater than 20, so it must be inserted after the 20. Complete the insert of 25. Item 25 is placed into the leaf node with plenty of room, easy peasy. Very important, make sure the node remains in sorted order. 20 to the left, 25 to the right. You have to maintain that order in every node. Make sure the node remains in sorted order after the insert. New insert of 43. Start an insert of 43, which is only slightly more difficult than the previous insert. Since the target 43 is not less than 30, stay in the root and go right. Continuing with the insert of 43, this is the find phase before the actual insert. I've got to find where 43 goes before I can insert it. Since the target 43 is less than 50, we go to the left child of 50. Move down the tree looking for a leaf node to place the item. Continue with the insert of 43. Item 43 will be placed in this leaf node. We've reached the leaf node. That's where we've got to do our insert. Very, very important. Just make sure the node remains in sorted order after the insert. Shift larger items than 43 to the right before the insertion. Continuing with our insert of 43, shift to insert the item into the proper position. Important, just make sure the node remains in sorted order after the insert. The 45 is shifted because it is greater than 43. 45 moved over. But the 40 is not shifted, it is less than 43. See how we opened up a spot to place the new item 43? Completing the insert of 43, 234 trees always insert into a leaf. Very important, just make sure the node remains in sorted order after the insert. The 43 was placed in the correct spot between 40 and 45. This is not hard, you just have to shift the larger items to complete the insert. Insert of 65. Start and insert a 65, which will not find room in a leaf. This will cause something called a leaf split. We are going to end up trying to place it here, but there's no room in here. So we're going to have to split a leaf node. Since the target 65 is not less than 30, stay in the root and go to the right. Continuing the insert of 65, which will not find room in a leaf, this will cause a leaf split. Since the target 65 is not less than 50, stay in the root and go to the right. But there is nothing to the right of 50. There's no item to the right, so go to the right child of 50, looking for a leaf. Continue the insert of 65. Split on the way down. What are we doing here? As soon as the insert algorithm finds a full node, it will perform a node split. The first step is to create a new empty node to the right of the full node. This is a leaf node, so we'll step through the leaf split algorithm. Here is the algorithm to split a leaf node. We will go through every step to complete this leaf split. First, create an empty node to the right of the full node. This is a new node that I'm going to create to the right of the node that I'm splitting. Move key C, the largest 85, to the new node. See that 85 that is red? It is moving over to this node. This is also known as key C, the third key in that full node. When you move key C, the largest 85, out of the full node into the new node, when the node is full, items need to move to make room for new data. Remember, we're still in the middle of inserting new item 65, so we're opening up some room in this node by moving the 85 over. Continue the insert of 65. We're making room in the full node. Next step, move key B, the middle 70, up to the parent, out of the full node and into the parent node. When a node is full, items need to be moved to make room for new data. Remember, we're still in the middle of inserting the item 65, and we're opening up some space to insert 65. Continuing the insert of 65. Only the small item remains in the formerly full node. Leave key A, the smallest 60 from this node, in the full node. Leave that alone. Leave key A, the smallest 60, in the full node. Not really a step, just leave it be. The full node now has room for new data. Look at all this space that can insert new items in it. We also have space over here for inserting new items. What we're doing is we're moving some data items to make room for our insert. We started this insert of 65 a while ago, and we're still in the middle of it, making some room available for 65. Continuing on with the insert, connect the parent node to the new child node. Adjust the child links in the parent node. Coming up here to the parent node and making sure the right child of 70 is referencing the new node. This is the easy case. Sometimes we'll need to shift some links if the new node is in the middle of this root. We still need to finish inserting the new item 65, but we have to adjust these links first. Continuing with the insert of 65, splits happen before the insert. After the split, we still need to finish inserting the new key. This all started when we tried to insert 65. We need to add the new key 65 into the full or the new node. Return to the parent node and decide if the new key belongs in the formerly full node, this one right here, or in the new node, this one right here. The new key 65 is less than 70, so insert it to the left child of 70. Here is the left child of 70. 65 needs to go there. Keys greater than 70 would have gone to the new node. Keys less than 70 go to the left child. Complete the insert of 65. Took lots of steps, but they're fairly simple steps. Item 65 is placed in the leaf node with plenty of room. There's plenty of room because we moved everything out of this. Very important, splits occur before the insert. New keys could have gone in the new node if it was larger. What does that mean? What if we were inserting 95? If we were inserting 95, we would have gone to this node and put it there. But we weren't. We were inserting 65, so we went to the left of 70 and inserted 65 there. Woohoo! Insert of the leaf node split is done. Before we do another insert, let's talk about why 2, 3, 4 trees have perfect balance. Binary trees add a new level by creating a new leaf. 83 adds a new level to this tree. 75 would add a new level to this tree. 73 would add a new level to the tree. Each new level that you add to a tree can imbalance the tree and slow its performance. Sometimes looking at something backwards yields a better solution. In 1968, a man named Dick Fosbury shattered the record and won the gold medal in the Olympic high jump. Up to then, athletes tried to jump forward or sideways over the bar. The Fosbury flop jumped backwards over the bar, and it worked much better. 2, 3, 4 trees add a new level at the root of the tree, not at the leaf level. When you add new levels at the leaf, you can unbalance the tree. We're going to look up here and add new levels to the tree up here. First, I want you to notice how easy it is to split a perfectly balanced 2, 3, 4 tree into separate trees with perfect balance. We started with one tree with a full root node and exactly 2 levels to reach the leaves. We now have 2 separate trees, the one with the root of 70 and the one with the root of 30. It turns out this works no matter how many levels a 2, 3, 4 tree with perfect balance and a full root has. You can split a 3-level tree into 2 separate 3-level 2, 3, 4 trees. You can split a 4-level tree into 2 separate perfectly balanced 4-level 2, 3, 4 trees. Now we just need to add a new level to the tree at the root. When you create a new level, create it up here. Do not, I repeat, do not create new levels at the leaf. Create new levels at the root. See what I did there? I added 50 as the root. It's a new level on the tree. The new level was created by adding a new root. If the 2 separate 2-level 2, 3, 4 trees are balanced, then the new 3-level tree is perfectly balanced. It takes exactly 3 levels to reach any leaf of this 2, 3, 4 tree. What do I mean by perfect balance? 1, 2, 3 nodes to reach 25. 1, 2, 3 nodes to reach 45. 1, 2, 3 nodes to reach 60. 1, 2, 3 nodes to reach 85. Down every path of the tree, we pass through exactly 3 levels. This is perfect balance. This is a small example, so it fits on one slide. But if you took a perfectly balanced, full root, 9-level 2, 3, 4 tree, you can split it into 2 separate and balanced 9-level 2, 3, 4 trees. Then add a new level to the tree at the root and it becomes a single, perfectly balanced 10-level 2, 3, 4 tree. A new leaf level can unbalance the tree. A new root level does not. Adding a new node down here can unbalance the tree. Adding a new root does not unbalance the tree. Insert of 80. Let's do an insert that causes a root split. Remember, we split on the way down. As soon as a full node is encountered, split it. This prevents a domino effect that works its way back up the tree. This is where we usually scan 30, 50, and 70 to find which child link to follow. Instead of that, let's preemptively split the root first before the insert. Split on the way down. Suspend the find/search and perform the root split now. Here is the root split procedure. Let's do this first before we try to insert 80. Split on the way down. The balanced 2-level search tree needs to become a balanced 3-level tree with a new root. I'm going to create a new root node, parent to the old full node. Here's the old full node. This will be the new root, the parent to that node. Node splits promote the middle item. We need a new root so we can promote an item from the old root node. This will be the parent when the current tree is split into separate trees. Split on the way down. All node splits need a sibling node. Create a sibling node to the right of the full node. Here's my full node. It needs a new sibling. There's the new sibling node. Node splits move the largest item to the right. We need a new sibling node to the full node so we can move an item from the old root. Remember our algorithm from before? A is the smallest key, B is the middle key, and C is the largest key. C needs to move over here, and B needs to be promoted. Splitting on the way down. Same as any split, we got to move the largest key. Move key C, the largest 70, to the new sibling. See why that's red? Because we're moving 70 from the old full root to the new sibling. Move the largest item C, 70, to the right to the new sibling node. Make room in the old full node. Splitting on the way down, you can now see the new 3-level tree forming. Let's continue on with the root split. Move key B, the middle 50, up to the new root. See this 50 right here? It's got to go up to the new root. Moving the middle item B, 50, up to the new root node, we make room in the old full node. What if this node here had to split and promote up? We want to make sure there's plenty of room to promote up if this node has to split. Once again, 50 is in red because it's moving to the new node and it's going to go away on the next step. Splitting on the way down, you can see the new 3-level tree forming. Continuing with the root split, let's leave key A, the smallest 30, in the full node. There's our 30. Leave it alone. Let it stay in the old node. Leaving the smallest item A, 30, right where it is in the formerly full node. Notice how the single node with 30, 50, and 70 split into 3 nodes. This is a root split. This node was full. The big item went over here, the middle item went up there, and the small item stayed where it was. One node becomes 3 nodes. Splitting on the way down, connect the new root. Adjust the child links in the new root. What did we just do? Connect the new root to its left and right child. 50, the new root, has to have its less than link go to the old full node. And 50 in the new root has to have its right link go to the new sibling. The left child will always be the old root, and the right child will always be the new sibling. Remember, we're still inserting 80 here, and we're splitting on the way down. Move the left/right children of 70. I'm down on this last step here. Move the 2 right children from the full node to the new sibling node. When 70 was in the old root, it had a left and right child. When 70 moves to the new sibling node, the children need to move with 70 to the new sibling node. 70 was the C item in this node. When it moved over, the left and right child of 70 have to shift over too. The red arrows show the old left and right children reference. 70 had a left child that pointed here. That left child had to move to the new sibling and point to the same place. 70 had a right child that pointed over here. That needs to move to the new sibling and point to the same node. Do you remember what started this way long time ago? We still need to finish the insert of 80. The last step of the root split is to complete the insert. We start at the new root and do a find and search to locate the leaf node 80 belongs in. Always insert into a leaf with a 2, 3, 4 tree. The new key 80 is greater than 50. We need to go to the right of 50. So go this way, searching for a spot to insert 80. Continuing with the insert of 80, find search to locate the leaf node 80 belongs in. Always insert into a leaf. The new key 80 is greater than 70. Go to the right child. What did I just do there? What I'm trying to insert is greater than 70. 70 is the last item in the node. I need to go to the right child of 70. Continuing the insert of 80, we have found the leaf node 80 belongs in. We must keep the node in sorted order. Insert 80 before the key 85. Shift the values in the leaf node greater than 80 to the right. Create room for the new key 80 in the leaf node. 85 shifted over to make room for 80 right there. Woohoo! Complete the insert of 80. It's done. We shifted 85 over and put 80 in its proper spot. But let's look at some hypotheticals here. What if we were inserting 47 and not 80? The split first means no domino effect. If I was inserting a 47, it would continue to this node, split it, but that wouldn't be a problem. Why would splitting this not be a problem? Because there's plenty of room in the parent to promote 43. I considered redrawing the tree to make it look more pretty than it does, but decided not to because the existing nodes in the tree do not change memory locations, so why change where I show them on the slide? Again, this could look a little prettier, but since these nodes don't have to move anyway, let's just move the links and leave the nodes where they are. What I did not show is a node split in the middle of the tree, because that would be very similar to the root split, but no new root. Once one of these nodes in the middle of the tree fills up, it's going to split and promote up. And that's how the root fills up. When these nodes split, items go up to make room. That's it for 2, 3, 4 trees. We'll see you soon.
Ginside.com.